Good morning, everyone, and thank you for coming to my talk. The title of my talk is Characterization of Domain of Fixed Stability Under Control Input Constraints. My name is Kunal Garg, and this work has been conducted under the supervision of my advisor, Danitra Panagu. So this is the outline of my talk. I'll start with introducing the concept of finite and fixed time stability. I'll present a motivating problem that would motivate why we need new results on fixed time stability, and then I'll conclude my talk. So, asymptotic and exponential convergence pertains to convergence as time tends to infinity, as we already know from our nonlinear controls class. On the other hand, the notion of finite time convergence requires that the system trajectories converge to the origin or the equilibrium point within a finite amount of time. Fixed time stability, fixed time convergence is a stronger notion where not only the time of convergence is finite, it's independent of the initial condition. So, irrespective of where the system trajectory starts, they always converge to the equilibrium point within a fixed amount of time. So more formally, for a nonlinear system whose equilibrium point is the origin, the author of the paper listed below defined finite time stability as follows. So the origin is said to be finite time stable if it is Lyapunov stable and there exists a settling time function t, which can depend on initial conditions such that as t tends to this capital T, system trajectories reach the equilibrium point. The authors also introduced the Lyapunov conditions to establish finite time stability. In particular, if this kind of a condition is satisfied along the system trajectories, then we say that the equilibrium point is finite time stable, and the settling time function t is upper bounded by this kind of an expression on the right hand side. And as we see, it depends on the initial conditions. Now, this upper bound on the time of convergence can potentially grow unbounded as the initial conditions go farther and farther away from the equilibrium point. So, a stronger notion of fixed time stability can be used, as defined by the author of this paper listed below, where the equilibrium point is called as fixed time stable if it is finite time stable and the settling time function is uniformly bounded for all initial conditions. So the authors also introduced the Lyapunov conditions to establish fixed time stability. In particular, if Lyapunov function v satisfies this kind of an inequality, where instead of 1, now we have two terms on the right-hand side, one with an exponent between 0 and 1, and one whose exponent is greater than 1, then the equilibrium point is fixed time stable, and the time of convergence, or rather the settling time function t, is uniformly bounded by this expression, which is independent of the initial conditions and only depend on these parameters alpha 1, alpha 2, and the exponents gamma 1 and gamma 2. So there has been a lot of work on finite and fixed time stability after the introduction of these notions by these two authors. In particular, authors of these papers listed here have used these notions for motion planning problems by utilizing the finite time or fixed time stability conditions in a quadratic program formulation, guaranteeing that the solution of those quadratic programs result into a finite time controller. Now, the problem with these papers is that under input constraints, there's no guarantee that the underlying quadratic program or the QP would be feasible. So that's the problem that we address in this paper. We consider a general class of control of fine nonlinear system, and the problem statement is given below. So we wish to design a control input that satisfy these kind of linear inequality input constraints such that the closed loop trajectories reach the goal set given as a zero sublevel set of a continuously differentiable function within a user-defined time TUD. Now we are concerned about linear inequality constraints because we are going to use a quadratic program which can only handle linear inequality constraints. And if we have infinity norm constraints on the control input, they can be readily represented using linear inequalities. But if we have one norm or two norm constraints, we can use equivalence of norms to again represent them using linear inequalities. All right, so a motivating problem is a simple one-dimensional control design problem where the objective for control design is to design a control input so that the closed loop trajectories of this one-dimensional system reach this goal set within a user-defined time where the control input is lower and upper bounded. A natural approach using quadratic program is to include the input constraint and the traditional fixed time stability condition proposed by Polyakov in this particular form. And if this QP is feasible for all x, then the solution of this QP would solve this objective. The problem with this particular quadratic program is that there's no feasibility guarantee because there are input constraints present in the system. Now, to handle input constraints, generally what is being done is introduction of a slack variable in the Lyapunov condition. So that is what we are going to do as well. So we introduce, instead of a constant slack delta 1, a product of the slack variable with the Lyapunov function v as a potential option. If we keep this delta 1 as a free variable, then we can show that this quadratic program is always feasible because we have two variables and two inequality constraints. But can we also guarantee that this kind of a Lyapunov condition guarantees fixed time stability? Let's see. So this is what we show in our paper. So if a Lyapunov function satisfies this kind of an inequality along the system trajectories, where instead of two terms introduced by Polyakov, we introduce this additional term where delta is kept as a free variable, then depending upon the relative value of this delta and with alpha 1 and alpha 2, there always exists a domain D, or what we call as domain of attraction of fixed time stability, such that starting from this domain, the system trajectories reach the equilibrium point or the origin in a fixed amount of time t, where the domain of attraction and the time of convergence both depend on this ratio. So what we achieve by introducing this new term in the upper bound of the time derivative of the Lyapunov function is feasibility guarantee when used in a quadratic program, and robustness with respect to a class of additive vanishing disturbance. So in particular, if the origin of the nominal system is fixed time stable and vanishing disturbance act on top of it, then the fixed time convergence is still preserved. All right, so the domain of attraction is essentially the domain where v dot takes negative values, right? So if this ratio delta 1 over 2 square root alpha 1 alpha 2 is less than 1, then the expression inside the parenthesis is always positive. And with v being a positive definite function, the upper bound on v dot is negative, and so the domain of attraction when this ratio is less than 1 would be the whole Rn. When this ratio is greater than equal to 1, then this expression is positive only in this red zone. It's also positive in the green zone, but it takes negative values in this blue zone. And so the domain of attraction for the different values of this ratio R is given here. In particular, as I mentioned, when this ratio is less than 1, then the whole Rn is the domain of attraction. And when this ratio is greater than equal to 1, then this red zone, whose expression is given here, would be our domain of attraction. And similarly, we can also compute uniform bounds on the time of convergence for these two particular cases. Finally, we discussed how we can use the new fixed time stability condition in control design. So to address the problem stated earlier, where we wish to design controllers so that the closed loop trajectories reach a goal set within a fixed amount of time, we use this kind of a quadratic program, where the first constraint is the input constraint for the given linear input constraints. And the second inequality constraint is the new fixed time stability constraint, where delta 1 is a free variable. Note that in the objective function, we also use a linear term with a positive coefficient to penalize delta 1 taking positive values, so that delta 1 not only takes smaller values, but we encourage delta 1 to take negative values as well. And as we discussed earlier, if delta 1 is smaller, then the domain of attraction would be larger. So if we denote the solution of this quadratic program as a function of x as u star delta star, then the domain of attraction, as we already discussed, would depend on the ratio of delta 1 and 2 square root alpha 1 alpha 2. And in particular, if we wish to find one domain of attraction, then we can take the supremum of this ratio over all x and denote it as Rm. And then if Rm is less than 1, then we know that the domain of attraction would be whole Rn. And if Rm is greater than equal to 1, then there would exist a domain D, such that starting from that domain, the closed loop trajectories would reach to the zero sublevel set of this Lyapunov function V. Now, how can we compute the supremum of this value? So to do that, what we can do is we can sample the state space and compute the value of delta 1 using a model in simulation environment and find the maximum value or supremum of this delta 1 over those sampled values to get an idea of how large this Rm would be. So with that, I conclude my talk. So we presented new results on fixed time stability, which encode robustness with respect to a class of additive vanishing disturbances, as well as guarantee feasibility when used in a QP formulation. We also discussed the relation of domain of attraction for fixed time stability as a function of slack variable or with the ratio of the slack variable and the constants alpha 1 and alpha 2. Future work involves guaranteeing safety for online learning along with fixed time convergence guarantees and designing consistent discretization schemes for these dynamical systems so that when we implement them for real world systems using zero order hold controllers, we can still guarantee fixed time stability. Thank you.